So let's start. So first of all, my name is David. You can see all the relevant information in the Moodle, like the email and where I'm sitting. So if you want to schedule a meeting, you can email me. Everything is fine. Second of all, it's the first time for me to teach in English, so I hope it will be fine. You will help me, be with Google Translate, and we can handle it together. I hope so. Some technical issues. So you have a homework you need to submit to the Moodle, the homework, and 2 quizzes during the semester. Okay, so total is going to be 30 or 33 points out of the final grade. It's the 2 quizzes and the homework. You have any question before we start? Okay. So for now on, and also you can see in stats this week we're only going to do like a review on thermodynamic, thing that you have already learned. So first of all, the basic thing that you know is that we have some function, S is a function of the energy, which we called it entropy. And in general, it's an increasing function of the energy, meaning that via the second law of thermodynamics, we know that delta S is greater or equal to 0. This is true if we have any adiabatic process, meaning we don't have a heat transfer. So the entropy is greater or equal to 0, the change in the entropy. And is equal to 0 only if our process is reversible. So if you can go from A to B adiabatically and then return from B to A adiabatically, so the process is reversible, so delta S, the change in entropy, of course, is 0. Because it should increase from A to B and increase from B to A, so the only option is it will stay 0. Reversibility, meaning that you can do it by reverse, like you can go from here to there without heat transfer and then go back. Okay. I think in Hebrew it's the same, so I don't know. תהליך reversibility, הפיך. And now we can have some kind of different energies. So we have free energy and different kinds of free energy, because for any process we need to use different parameters. So some free energies, the natural parameter are the temperature and like the temperature and the entropy, and for other free energies the natural parameter can be the volume or the pressure or other things. So depending on our exercise, we need to use different thermodynamic parameters. So for example, we have the Helmholtz free energy. Which is F equal to E minus Ts. And what is meaning? It's meaning that in some process, like in thermodynamic process, it's not true that the system tries to have minimum energy like this energy, or maybe I'll write it as U minus Ts. U is the internal energy. So it's not true that always U need to be minimized. Like in mechanics, that we said, okay, the energy is supposed to be minimum. Here, the free energy is supposed to be minimized, and there is competition between U, which is the internal energy, and the entropy. So sometimes the entropy can win, and the system said, okay, I prefer to be in maximum entropy, because the entropy is increasing, so I prefer to be in maximum entropy than to be in minimum energy. So F need to be minimized, not U. This always the case in thermodynamics, that we have some competition between the energy and the entropy. So it's so the entropy is a new different function or new different process that we don't know it till we study thermodynamics. It's a new invention. And the last thing, we can have some relation which is called Maxwell relations. Which are some relation between the different energies and thermodynamic parameters. So we can see it in Wikipedia, you don't need to remember it. I never remember it. We'll write some two relations just to see it. So we have, for example, the S over the V with, when T is constant, is equal to the P over the T. When V is constant, which is equal to okay, this is one example. So you know, so we can see that if we want to calculate the second derivative of F, the Helmholtz free energy, so it equals to the S over the V or the P over the T, where S is the entropy, V is the volume, and P is the pressure. And you have a lot of those kind of relation. You don't need to remember it, it's just an example. Hey, you have any question? Everything's fine? Okay. So let's have an exercise. Maybe I start it on the next board. From left to right. So we have an elastic rubber. A gumi, elastic. With the tension, T is the tension, J is the tension, sorry, J is tension, L is the length, and T is the temperature. And we also know that we have a function G, which is a function of T and L, and it's the derivative of J with respect to the temperature, which is equal to this expression. And F, the function of T and L, which is the derivative of the tension as a function of the length. Okay, so write it down. It's just this, you can think about it, it's fine experimentally. Okay, experimentally you do an experiment and then you find that the tension is changed with the temperature like this, and is changed with the length like this. And we define it as two functions, as G and F. That's it. Okay, well, L naught is just the loose, the rubber when it's loose. Okay. Okay, we're fine. So the first thing we need to find out is the equation of state. שקוראים בעברית משוואת מצב. Okay, equation of state. That J is a function of T and L. Okay, we want to see what is the relation between the three parameters. So we start with J. This is the definition. But we can see here the J is not depending on the temperature. Okay, it's only dependent on the length, not on the temperature. So G. G?
Yeah, G.
Ah, sorry, G. Yeah, sorry. So G is temperature dependent, independent. So we can write it as G dt is a full differential, and we can just say, like, we can integrate it on both sides because G is only depend on one parameter, so we can integrate it on both sides to get the J equal to G as a function of L times T plus a constant that can in general be length dependent. Okay, this is true only because it's T independent, so we can write it as a full differential. In addition, you can check that dg over dl equals f over t. Okay, if you take g and you take its derivative with respect to L, you get exactly f up to the temperature dependent there. So we can do again the same game to obtain this j equals to g over LT plus some constant. This can depend on t. To this?
No, the first one.
You can check it. Like, just take g, take the derivative with respect to L, then you can see that you get exactly f up to the t. Okay, you can just check it. Don't want to get over it now, but good. So we have two solutions for J, and we can compare them. And if you compare them, you can see they are exactly the same up to the constant. Okay, but we have one constant that is L dependent and one constant that is T dependent. And they need to be the same, so it should be just constant which is independent of any parameter, right? Because we can compare them, so R1 as a function of L need to be equal to R2 as a function of T, so they have to be equal to some constant R. So now we can write J, which is equal to GL times T plus a constant. We have the definition of G there, so it's ALT over L naught, 1 minus L naught over L to the third, plus a constant. And now, how can we find a constant? What's the condition it needs to satisfy? J is a tension, right? So if L equals L naught, what the tension should be? Obviously, 0. Okay, because if we're in the loose position, we didn't stretch the band at all. L equals L naught, there is no tension. There is no tension, J needs to be 0. Okay? So J will L equals L naught equals 0, meaning that R equals 0, meaning that J is ALT over L naught this is the final answer for the tension. Now the equation of state. Have any questions? Okay. In addition, it is something that we need to use later. J equals to JL times T, meaning that if J, we can plug in G, so J over T equals G, and if we plug in G only, the definition is the J over the T with L constant. Okay, I just state it now because we need to use it in the next ahead. So. Okay, now the question is, so B, let's write it in below. Okay, so we stretch the rubber band now adiabatically and reversibility, in a reversible way, I don't know. Say it reversibly. Reversibly? Okay. From L naught with T initial to L final. What will be T final? Okay, so we stretch it. We start from L naught with some temperature. We don't know what. It's some T initial. We stretch it to some length, L final, and then we want to know what is T final. What is the final temperature? And it's done adiabatically, so we can use the second law of thermodynamics and reversibly, so we use it later. Okay, so first of all, we write the equation of state, or the equation of the law of thermodynamics. So if we are in general thermodynamic process. So we know du is equal TdS. And if we are done work on the system, so we need to add PdV, which is the pressure time the infinitesimal volume. But here we don't have pressure or volume, we have the work done on the system. The work we done is to stretch it. So as we define work in Newtonic mechanics, so we have J, which is the tension, time, and infinitesimal length. Okay, we have J dl. Infinitesimal length. Yeah. Okay, because we are doing work on the system. We're stretching the rubber band. Well, so we can go to Helmholtz free energy if we know F equals to U minus Ts, meaning that dF equal du minus TdS minus S dt. So we plug in du, so TdS and TdS are cancelled, and we have that this is equal to J dl minus S dt. Now you know how full differential works, you know how to work with it. Like if I ask, okay, what is J from this equation? What? So if you have full differential, if we know that, let's for example, you have some general function, just for clarification, if you have a general function, set f, okay, and we know it's, for example, depend on T and L, okay, this is just an example for a full differential. So df by definition, it's df dot t dt plus df dot l dl. Okay, this is always true. If you have some function and you want to represent it as a full differential, so the full differential is the derivative with respect to any of its parameters, and then d the parameter. So now we can recognize here, so if df equal to J dl minus S dt, we can say, okay, so if we will write it in a full differential way, J should be df dl, and S should be minus df dt. Oh, this should be large T. It's the temperature, it's not time. Is it clear? Because it's important. If you have a question, it's a good time to ask. Okay? We write something, if we have something in full differential, we can always identify this as the derivative of the function with respect to this parameter, and this is the derivative of the function with respect to the second parameter. This is just a mathematical definition. Okay. Everything that I'm doing is just to prove one concept. I want to use the heat capacity. So I want to prove this, that the energy, it's only a function of the temperature and not of the length. So I change parameter, we start with u, but I change parameters to j and s because I want to check du over dl, where t is constant. And I want this to be 0, because if it's 0, it means that u is just parameter of the temperature, and then my heat capacity, that I need to use it, it's defined. Because always heat capacity is meaning that you have some u equals to some constant time dt. So if it is true and u only depend on the temperature, so I can define what is the heat capacity, which is a constant. So let's see, so du over dl, so it's, where is the definition? The definition is there of u, so it's just t dou s over dou l with t constant plus j. Found the definition here of u. But let's check what is dou s over dou l. So we have the definition of s there. So it's minus, so dou s over dou l, it's minus dou le dou l, dou over dou l of dou f dou t. Okay, this is from the definition here of s, of the entropy. And of course, because everything is smooth and nice and all the functions are behaving like I want them to behave, I can switch between these two derivatives. So it's minus dou over dou t, dou f over dou l. And dou f over dou l is j. So it's minus dou j over dou t. Where? J? Here? G is the function we defined in the first, which is just the derivative of j with respect to t. Okay, it's just an experimental function we found. We check how the tension is changing with the temperature, and we saw it's some function, we call it g. Okay? So let's plug it in. Here, the u over dou l when t is constant, it's t time this, so it's minus t time dou j over dou t, plus j. But as you see here, it's this why I wrote it is there, because we now use it. J equals to t over dou j, t times dou j over dou t. So we can say plus t dou j over dou t. Okay, this is j. As we can see there. And it's equal to 0. So u only depended on one parameter, on t, because it's L independent. So we can write it in the full differential as du is some constant times dt. This constant, we call it the heat capacity, which is in constant length. Okay, you can define heat capacity with various parameters. So now it's the heat capacity with constant length.
So if the heat capacity at
Yeah, always the heat capacity need to be defined with something constant. So generally in thermodynamics you write CV or CP, but here the length is the parameter, so it's in constant length. Because U, it's only dependent on the temperature. Okay, not so you can write it always as a the full differential like this. This is the most general way. And what you define it, here should be like du over dt. So we defined it, du over dt is a constant because it's t independent, so it's just some constant CFL. Okay? Good. So I think Stas will be doing a lot of this game of full differential, and then you are identified all the prefactor as a derivative or something, and then you play along. Maybe you did it also in thermodynamic 1, because this is how you get all the Maxwell equation, Maxwell relation and everything. So now let's find the entropy. So what is the entropy? From here, we can plug in du as CL times dt. So we have CL times dt equals TdS plus JDL. When we find J, it's only G times T. So we can write it as a function of ds. ds is CL over T dt minus GL dL. And don't be intimidated by all the process. It's not something you need to think about it by yourself. Okay, it's just an explanation, it's an example. I don't think that I would think about it by myself, like to change, to switch from the energy to Helmholtz and then prove that U it's T independent, and to define the heat capacity and then go to the entropy. Okay, it's not something so you might think about it, but it's just an example how you can use it, and also in the end we're going to get a nice result which echoes to something you are going to do in your homework. So this is the main idea of this exercise. Okay, so don't say, oh, we didn't think about it, right? Me too, I wouldn't think about it also. So the nice thing to get this kind of function, that we have one thing that is dependent only on t, and the other thing that's dependent only on L. So we have this function which is dependent on two parameters, which aren't related to each other. And now you need to believe me, or you need to be convinced that if we have this thing, we can integrate on both sides with each one in a different, each one we can integrate only on these parameters. Meaning that if I want now to see what's the difference in the entropy for one side for one point to another, I start from, like, imagine I have some manifold which is dependent on L and T. Okay, so I can go one direction, only change the length, another direction, only change the temperature, and all the intermediate direction, I change the temperature and the length. And I want to go from one point to another. Okay, so I will need to integrate on all the infinitesimal ways in the middle, and because every part is only dependent on one parameter, I can tune it so I can integrate, so the course that I'm doing it doesn't matter. So I can go like this or go like this. It doesn't matter. So I can do everything by itself. I can think about it as I take constant t and move on the L direction, and then constant L and move on the t direction, and I get to this point. Okay, so I can go like this, and I can go like this, and I can go however I want, but I can do it independently because this is dependent only on t and this only on L. Yeah.
You are missing the t in the second side of the equation. J equal T GL.
J equal GDL. No, it's fine. What is J? Yeah, I think it's fine. Are you agreeing or not? Ah, okay, so it's fine. Okay, so I hope I convinced you. If not, think about it. It's not trivial, okay? It's not something trivial. So you can write it so you can say the ds, delta s, sorry, so the difference between one point which has some t initial and L initial to t final and L final. So the difference in the entropy between these 2 points is just to integrate over the first term and plus an integration on the second term. Okay, so I write it generally, some T1 and T2, L1 and L2. And if you do this integration, you can plug here G, as I defined in the first time. So you can plug it in and do the integration. And the result is CL time ln of T2 over T1 minus A L naught of H where H of X is defined okay, so this is the result where H is just a function. Just to write it simply, we define a function H which look like this. And this is the important thing that's as X is increasing, H is also increasing. Okay, it's an increasing function of X. That's the only important thing. Oh, I have a problem. Wait. No, it's fine. No, here it should be, sorry, here it should be a naught. Sorry. Okay, it's L2 over a naught minus L1 over a naught. So if you agree that this process is correct, the integration is trivial, okay? You know how to integrate. And now we can plug everything in. So this is general, and in our problem we are starting from L naught, and so L1 it's L naught, and L2 it's L final, and T1 and T2 is T initial and T final. In addition, we have another condition when we started, that is a reversible process. So if it's a reversible process, as I said in the beginning, delta S is 0. Okay, because we're assuming it's reversible. Okay, this is the condition of the problem. We said it's an adiabatic process with no heat transfer, and it's reversible. Okay, this is how the problem is defined. So delta S, it's 0. So we have the CL time ln of T final over T initial equals to A L naught H of L final over L naught minus H of L naught over L naught, which is just 1. And now you probably forget why we started all this. We want to find the temperature, the final temperature, so we can extract the final temperature from here. Okay, you divide it by CL and exponent both sides. And the final result is TF equals Ti exponent of all this. So this is the final result. It's very easy to interpret it physically because this is just a constant, all these are just a constant. This is, h of 1 is also a constant, so when you are stretched and the LF gets greater than L0, so LF over L0 get greater than 1, so it's also an increasing function of L final. So you have an exponent which is increased. So if you stretch the rubber band, and if you assume that this stretching it's adiabatically and you can do it reversibly, so the temperature is increasing exponentially. Okay, again, this is an increasing function of LF, and the others are just constant. So no matter what temperature we start it, if you're assuming the two things we assume in the beginning of the exercise, it's the reversible and the adiabatically, you can stretch it and the temperature is going up exponentially. Okay, is it clear? You have any question, I don't know, regarding specifically how we got it or generally about the physics or the thermodynamic processes? Okay. So this is nice, but what equivalent to what you're going to do in your homework is the last section. So we started by finding what is the equation of state. We found how the tension is depending on the temperature and on the length. We then find the final temperature. And now you say we stretch the rubber band, now we leave it. Okay, so you leave the rubber band. Assuming there is no heat transfer. To the environment. How you write environment? Environment. You have a mistake? Yeah? Nice. I didn't practice. Shit. Okay. Environment. Okay, good. Okay, so 90%. So there is no heat transfer to the environment. And the question is, how is the temperature and the entropy changing? Okay, so we stretch it, now we leave it. We just go back to its loose position. And we are assuming there is no heat transfer to the environment. And we ask, okay, how is the temperature and the entropy changing now? Okay, so let's start from the easy part. How is the temperature changing? Yeah. Okay. So let's think. There is we just leave it, so no work down on the system. And there is no heat transfer. Okay, but U in the first law of thermodynamics, the most basic one, so U, it's supposed to be a combination, the energy is supposed to be some combination of the work done on the system and of the heat transfer, or the heat, Q plus W. Right, so it doesn't change. Because there is no heat transfer, no work is done on the system, the energy is not changing, and we see this, the energy depends only on the temperature, or the temperature depends only on the energy, okay? U equals to some constant T, so the one dependent on the other, so if the energy is not changing, the temperature is not changing. Okay? No, but the entropy can change. No, there is no work done on the system, but yet the entropy can change. Let's calculate the entropy. We have the, I'll delete it. Here, good.
There's no process going on.
No, you leave it, okay?
Yeah.
You just leave it and then you go back to this loose position. Okay, you just,
First it's stretched out.
yeah, you stretch it and now you leave it and it goes back. So assuming what we assumed, there is no change, the temperature is not changing. Okay? But how is the entropy now? So the entropy, if you look in this solution we got earlier, now we just need to plug in the different parameters. So now T1 and T2 are the same because the temperature is not changing. And we need to switch between L2 and L1 because we started from, like our starting position was L2 because we started from the stretched position, and we finish in L0 because we finish in the loose position. So L2 now equals L final, and L1 equals, L1 equals L2, and L2 equals L0. So delta S is just 0 minus A L0 of H L0 over L0 minus H LF over L0, which is this. Okay, so again, we use the same equation, but T is the same, so the line vanishes. Here we finish at L2 when we stretch it, but now it's the opposite. We are finishing L0. So this is here, come here, and we start from L1, but now we are starting from L2 because we are starting from the stretch position. So we get it, and again, because it's an increasing function of LF, so no matter how we stretch it, if we stretch it more than L0, this is greater than 0. So no matter how we stretch it, when we leave it, the entropy is going to increase. So in the homework you're going to have some exercise which is related to you need to calculate the Joule-Thomson effect. And the Joule-Thomson effect is very similar. You have some ideal gas. And you can calculate, and you will calculate it in your homework. That's when you let the ideal gas spend. Okay, you have some coefficient of Joule-Thomson coefficient. You can see it. And when you let the ideal gas spread, okay, you just take some bar out and just spread. So you have no change in temperature, but you do have change in the entropy. And of course, it makes sense. You have more state now. You put the ideal gas here, and now you let it expand freely. So you have more space. Of course, the entropy is going to increase. But because in ideal gas and there is no interaction between them, it doesn't care if it's in very small volume or very large volume if you talk about the temperature. Okay? Because it's just an ideal gas. The particles are not speaking with each other. So if it's in small volume, there is some temperature. If you let it expand, it's the same temperature. The particle doesn't interact with each other, and it's not helps them. So, the temperature is not changing, but the entropy do. So it's equivalent to what we saw here. So if you stretch it and then you leave it, the temperature stays the same, but the entropy can decrease. So it's two different processes, and this is also more magnified the importance of the entropy, which is a new quantity that we didn't know up to the thermodynamics, have some interesting properties or non-intuitive properties, and it's not dependent necessarily on the temperature or on other parameters. Everything can be the same, but yet the most basic thing, or the most basic concept in thermodynamics, that the entropy is increasing. Do you have any question about what we did? Okay, so that's it.